Okay, we're going to try to fly through solutions to the multiple choice part of the physics take-home test for circuits. So take a look. First one says, hey, when lighted, a 100-watt light bulb operating on a 110-volt household circuit circuit has a resistance closest to. And so I'm just going to think about that as being, let's see here, 100-watt light bulb, 110-volt current, or circuit. So you're saying, hey, 100 watts, that's my power, right? And you say 110 volts, that's my delta V. And you say, well, I've got a relationship between power and delta V, and we're trying to find resistance. You say, well, I know that power is delta V squared over R, okay, is that formula. Is that one on the AP formula sheet? Not sure. But that's one of like three forms for it. Basically, I think this is the one that's on the formula sheet, is current times voltage for power. And I can just use delta V as IR and substitute around and get it to this form, which is the one I need with these three variables. It's also I squared R. So anyway, so looking at this one, you say, hey, I'm trying to find the resistance. So just moving this here, you're like, hey, R is delta V squared over P. And that delta V is 110, so it's 110 squared over 100. And you're like, yeah, that's roughly, very roughly 100. So 100 ohms is what we're looking for, and that is choice E. So for problem 1, I would say E. All right, problem 2. If I is current, T is time, E is electric field intensity, X is distance, what's the ratio of this to this? So integral of current dt, you say, well, wait a minute, I know a relationship between current and time. That is that I is dq dt. So if I rearrange that and integrate, that's just going to be my q, right? So this is just charge, right? And you say, they want to know what units to be expressed in. So charge, that's going to be in coulombs, okay? And you say, my ratio of that to what? This is integral E dot dx. Hopefully you recognize that one, actually. And you say, oh, E field through a distance. You're right. That's my delta V. And so that would be in volts. And you say, hey, coulombs per volt. Hey, that's the unit for capacitance. That's a farad, is a coulomb per volt. So D is the answer I want for 2. All right, 3. In the circuit shown above, what's the resistance R? And so take a look at this. I'm just going to go ahead and do a Kirchhoff's loop law on this. Let me go around this left loop like this. Do you see that there's an arrow showing the currents going this way, and an arrow showing the currents going this way? 1 amp this way, 2 amp this way, junction law, currents in equals current out. I've got 3 amps going through that resistor there. So I'm going to go ahead and do a little loop law on this left loop. Starting at the low side of the battery, going around clockwise. So first I'm going to go up 16 volts from the low V to high V side of the battery. I'm doing my delta V loop is 0. So I'm going to go up 16. If I have 1 amp flowing here, I got 1 amp flowing through all this. So 1 amp through 4 ohms, I'm going with the current. So I'm going to go down 4 times 1, right? I times R, right? 1 times 4. And then I'm going to go down. We know that there's 3 amps through that. 3 amps through R ohms, right? And then I'm back to the start, so that adds to 0. I can do the same sort of thing for the right loop. This time in this loop, I've got 2 amps flowing in. I'm going to start the low V side of the battery and run around this way. So I'm going to go up 24 volts. And then I'm going to go IR, right? Down IR. I'm going with the current. 2 times 6. I'm going to go down 12. Sorry, I'll write that as 2 times 6. Sorry. 2 times 6. And then I'm going to go down 2 times R. Oh, sorry, 3 times R. Okay, so looking at this one, 16 minus 4, that's 12. 12 is 3R. 12 divided by 3, just 4 ohms is R. I could do the same trick here and say 24 minus 2 times 6, 24 minus 12 is 12 is 3R. Again, I'm getting 4 ohms. Either way, either side that I loop law, I can get the resistance is 4. So B is the best answer for problem 3. Okay, here I've got a 12-volt storage battery with an internal resistance of 2 ohms being charged by a current of 2 amps. See, we're pushing the current backwards through that battery. We're recharging the battery. A current of 2 amps as shown. Under these circumstances, a voltmeter connected across the terminals from either side of the battery, what would it read? Well, I'm going this way. If I go this way, right, I'm going to go from high to low. I'm going to go down the 12 volts of the battery, right? But then I'm also going with the current. I'm going to go down IR, 2 amps through 2 ohms. So I'm going to go down 12 volts and then down IR. So I'm going to go down 2 times 2 ohms. So that's going to be a total of, I'm going down 16 volts going through that guy. So the delta V across this battery would be 16 volts. So E is what I'm looking for. Number 5. It says, I've got this circuit. I see I've got a battery, a switch, a resistor, and a capacitor. In this one, the capacitor is originally uncharged. At time 0, we close the switch. So we're turning the circuit on, and we're going to start to charge up that capacitor. And tell you the base, natural log base is E. Okay, in case you're wondering, that's what they're going to symbolize it. Which of the following is true at time t equals RC? So you should recognize that t equals RC. That's the time constant. You say, hey, what's the time constant? The time constant, that's tau. That's the time that makes the exponent simple in the expression. As we're charging up a capacitor, this is a case where I know I'm going to start with 0 charge and build up to a maximum charge on the capacitor. That's the one that looks like this, right? The graph. Asymptotic to some final charge. And I might remember then that like my, and so likewise they're asking here about current and voltage. So the current is going to actually do the opposite. The current's going to start at max and drop down. So actually current is the one I'm interested in, or voltage across the capacitor. You say voltage across the capacitor would slowly build like this. This is what the voltage graph would look like too. Okay, so let's do this, the voltage across the capacitor. So what I'm asking is, they're asking me questions about what those would, what's going to happen. The time constant is the time it takes for you to get to 63.2% of the max value here, right? So when time is the time constant, I'm at 63.2 of that, of my Vmax, okay, is where I'm at. That's this value here. And this one, I'm dropping down, so it's going to be I'll be at, when I'm there, right, at that same time constant, right? These didn't line up, but you get the idea. At that same time here, right, for that time constant, it'll be at, what's 1 minus 0.63? I'll be at 0.368 of the maximum I. Because what's this going to be? My expression, you might remember that exponential looks like a minus t over RC, right? And it might be, depending on which one we're looking at. If I'm looking at this one, yeah, this will be like my I is my I max times e to the negative t over IC. So at time 0 to infinity, at time 0, it's going to be e to the 0, it's 1, I'll be at the max at time 0, and it's head to infinity, e to the negative infinity, that's going to be going to 0, and I'll get 0. So this is the one that goes with this graph. This one, when I do the voltage one, that's going to be the one that is going to be my Vmax, right? Then it'll be the 1 minus e to the negative t over RC, right? So this is the one that we're from time 0 to infinity. Like I said, this one starts at 1 and goes to 0. This one, which is going to be the voltage equation, it's going to start at 0 and go to 1, right? Because e to the 0 is 1. 1 minus 1 gives me 0 for this expression, right? So anyway, so the point is, that's a long way of saying when I'm at the time constant, I should know that I know this is the one that's building up to a max, and I know that that's the one that's 0.632 when I'm at the time constant. Okay, that was a long way of saying that. And I know this one's when I'm going to be at 0.368 when I'm at the time constant. So here we go. If what this current is, delta V is IR. So the max current is when I would have delta V is IR rearranging. The I then would be EMF, the voltage over R. So EMF over R is that max current. So when I'm at the time constant, again, that tau makes this just minus 1. E to the minus 1 is 1 over E. So I have 1 over E times EMF over R would be the current, would be what I would have at the time constant. And that is actually right away choice A. So A is actually the one I want. Gosh, that was a much longer explanation than you really needed for that. Sorry. Okay, moving on. Let's go to the next one. Flip page to question 6. All right. Okay, hey look, we got a whole bunch of little circuits, little DC circuits, just a bunch of resistors and a battery. So as I'm running through this, it says, hey, the batteries in each of the circuits shown are identical batteries, so we're going to have identical voltages. And the wires have negligible resistance, so it's just the resistors here you're worried about that they show. Which circuit is the current the greatest? Which circuit is the equivalent resistance the greatest? Which circuit dissipates the least power? I'm going to answer the second question first. Let's find our total resistances. Hey, this is a 2 and a 2 in parallel, so it looks like A is a 2 and a 2 in parallel, so that's 1 over 2 plus 1 over 2 is 1 over the total, right, when you're in parallel. And so a half and a half, that's 1, flip it, it's still 1. This one has a resistance of 1 ohm. B, that's a 4 and a 4 in parallel, so that's a 1 over 4 plus a 1 over 4, right? That's a 2 fourths, flip it, that would be 2 ohms. C, it's a 2 and a 2 in series, so just add them, that would be 4 ohms. D is just a 2 ohm, and E is just a 6 ohm. So that's the resistances. So which one has the greatest? Well, that's the 6 ohm one. That would be E, would be the choice for problem 7. All right. Okay. What about 6? Which circuit is the current the greatest? Well, to find the maximum current, you're going to say, hey, I know that delta V is IR, right? All of the circuits have the same delta V. So the current is what I want to know. So current would be delta V over R. All of these circuits have the same delta V. So it's just whichever one has the smallest resistance would have the biggest current. So hey, the smallest resistance, that was A. So A has the biggest current. Okay. 8. Gosh, this marker is terrible too. 8. They want to know which circuit dissipates the least power, the smallest power. You say, okay, what's power? Well, let's see here. Again, this is the one I have just memorized, as P is I delta V. And you say, hey, do I know the delta V is the same for all the circuits? So whichever one has the smallest current, that's the one that has the smallest power, right? Because delta V's are all the same. Which one's going to have the smallest current? Here I asked which one was the biggest current. So just going through, the smallest current is the one that's going to have the biggest resistance, and that would be E. So E is going to have the smallest power. All right, so that's my answer there. All right, going on, question 9 says, hey, I've got this circuit, battery, capacitor, resistor, nice little RC circuit, switch. Assume the capacitor starts off uncharged. These graphs could be different things. We're going to ask, here's some options. So first, which graph would be the voltage versus time when I close, after I close the switch, after I turn it on? When I turn it on, you say, I want the voltage across the resistor. At the first instant, the capacitor is going to like not stop the flow at all because it's got to start charging up the plate, right? And so electrons will start flowing off the plate to the high V side, and electrons will start flowing this way, then attracted by the positive charge starts building up on the left side. It'll start attracting electrons there. So current's going to flow here, and this isn't fighting the current at all, right? There's no charge built up to resist the flow. So this is going to have the maximum flow at the first time. But as it starts to build, it's going to be harder and harder to push more charges to the plate, and so that current is going to die off, right? And it's in asymptotic heading to infinity. As in head to infinity time, it's going to drop off to 0 current. It'll act like a break in the circuit at the end. So we clearly want this shape graph. Okay, the other possibility is talking about going, yeah, that's the only one. So one is A for problem 9. Okay, problem 10. Here, oops, let me not go too far off. Problem 10 wants to know which graph represents the current versus time. Wait, isn't that what I just answered? I just had voltage across the resistor, right? Yeah. When I have big current, I get big voltage. So across the resistor. So this is going to be actually the same thing: voltage across the resistor and current across the resistor. Sorry, I think I answered this question first, but it's going to be the same. So 10 is also A, right? Which one's going to represent the voltage across the capacitor? Well, the voltage across the capacitor starts off being 0. There's no charges on the plates, but as it builds up charge on the plates, it's going to approach a final voltage. That's going to be graph B. All right, so that's what those look like. All right, that's that page. Let's see here. Grab a sheet of paper. All right, question 12 here. Okay, this capacitor is first charged by throwing the switch to the left. So you see I hook it up over here to where the battery is. So I'm going to start charging this. It's not connected here, so this isn't part of the circuit yet. So I'm just going to charge that capacitor, and then I'm going to discharge it by throwing the switch to the right. So then I'm going to connect the capacitor just to this resistor. Okay, so current will start to flow this way onto the plates, and then when I close the switch here, it'll discharge around that way. What they want to know is what's the time constant for discharge. You say, well, you should just know that in an RC circuit, again, I know I'm using the same thing twice on this test, sorry, that the time constant, tau, is R times C. And so if I want to increase the time constant, then I need to increase the resistance or increase the capacitance. We'll put another capacitor in parallel with C. In parallel, does the capacitance go up or go down? And you say, well, if I put them in parallel, then the capacitance actually increases. And so you say, oh, so that would work. That would increase the time constant. It makes sense. It's going to take longer to charge up the capacitor, or longer to discharge it. The more capacitance you have, the more you got to drain out. So A actually makes sense for that one. Let's just double check I'm not right. Putting another capacitor in series, that actually decreases capacitance, so that's not going to work. Placing another resistor in parallel, that would reduce the resistance, that's not going to work. Increasing the battery voltage, decreasing the battery voltage. The battery voltage has nothing to do with the time constant, right? The time constant just depends on these. Any circuit I slap that resistor and capacitor into like this, no matter what battery I hook up to it, it's not going to affect that time constant. It's going to be the same shape graph. Okay, next, 13. Two resistors of the same length, both made of the same material, connected in series to a battery. As shown, resistor 2 has a bigger cross-sectional area. Sure, it's fatter than I. Which of the following, the first one, which of the following quantities has the same value? So these resistors, right? And they're asking about the voltage between the ends of the resistors, the field strength inside, resistance. I'm going to start by thinking about resistance, okay? Let's figure this out. These resistors, the formula for resistance of a resistor is rho L over A, where this is the resistivity of the material, but these are made of the same material. The length, these are the same length, so that's not going to matter, but A is different. So they're going to have different resistances because they've got different cross-sectional areas. The one with the bigger cross-sectional area has a smaller resistance. It's easier for charges to get through the big fat guy. They got to squeeze the narrow guy. This one has more resistance than this. So the question is, what's the same? Resistance is not the same. Delta V between the two ends. Well, these guys have different resistances, but they'll have the same current flowing through because they're in series. And you say, well, delta V is IR. I have the same current flowing through them, but different resistances. I'm going to have different voltages. So that's not the same for both. Electrical field strength within the resistor. Electrical field strength, I'm going to think about the voltage thing and say delta V is negative integral E dot D dr dl, right? Well, if I have this uniform E field inside each, you say, well, look at this, it'll be E times the length. These guys have the same length. They've got different voltages though. They'll have different E field strengths in them. So that's not the same for both. Current per unit area, that's the current density, right? Which is sometimes called J, my current per area. How densely packed it is. Well, it's the same current in this guy as in this guy, but the current's spread out over a bigger area here. It's not the same current density. The only one left is current, and yeah, we kind of said, oh yeah, as much charge as flows in this guy is going to flow out the other side and flow into this guy and flow out the other side. So the current's the same for both. So E is the only one that makes sense. 14. The EMF of a battery is 12 volts. If the battery delivers a current of 0.5 amp to a load, the potential difference between the terminals of the battery is 10 volts. So I've got a battery, right? And they say, hey, this thing is supposed to be a 12 volt battery. But when I have this thing running, and I'm delivering 0.5 amp right, out to some, you know, external junk, right? When it's running through there, it says the delta V measured across the battery is only 10 volts. Why? Because there's internal resistance in the battery, kind of built in that you can't get around, and this little resistance in the battery is I'm gonna burn off some energy in that battery. So I'm gonna go down the voltage, some voltage at the intern of this guy, and up the 12 to get this overall change of 10. So I'm gonna go down 2 volts going through this guy. You say, wait, I'm going down 2 volts. And you say the current going through is half an amp, right? 0.5 amps. You say, oh, what's that internal resistance then? You say, well, delta V is IR. And so you say, okay, 2 is a half times R. R had better be 4 ohms. So that internal resistance is 4 ohms. That is choice C. All right. Takes me to question 15. The power dissipated in a wire carrying a constant electric current I can be written as a function of I, the length of the wire, the diameter, the resistivity. Okay, power in a wire with a current. The first thing that comes to mind is P is I squared R for me. Because they're giving me information about like the length of the wire and the diameter of the wire. That makes me think about that resistance is rho L over A formula. You know what I mean? What they want to know is, in this expression, the power is directly proportional to which. So this is going to be I squared times rho times L over A. And you say, hey, look, there's, is my power directly proportional to current? No, that's current squared, right? Is my power directly proportional to the resistivity? Yes, it is. Is my power directly proportional to the length of it? Yes, it is. Is my power proportional to, let's say it says area, well, I'm inversely proportional to area. The area would be, you know, some function of the diameter of the wire, right? It'd be like, if it was a wire shaped cylindrically or something, it would be like, cross section, what am I doing here? Crossing area would be just like, you know, proportional to that, well, diameter squared, really. It's like radius pi r squared, you know, it's going to be proportional to the diameter squared. So that's definitely not a direct proportion between power and that. So it's really just directly proportional to rho and L. That looks like choice C. All right, I put that up there, sorry. Let's see, one more on this page, problem 16. And that one says, hey, I've got this circuit. Ammeter in the circuit is connecting across here. And it says, if that ammeter reads 0, what would the resistance be of this unknown resistor here? So current's flowing in, it comes in here, and then it's going to split. I want to have no current through the ammeter, for the ammeter to read 0. The only way there's no current is if there's no delta V here. So the V value here and the V value here have to be the same. Now we know that as I go through this, I got to have the same delta V from here to here, no matter which path I take, around the top, around the bottom. So I know that whatever my voltage here, when I do going from here to here, there's some delta V. It's got to be the same delta V going this way or this way. So like for this path, how do I want to say this? I know I've got to go proportionally down the same voltage from here to here as I do from here to here, right? And from here to here, it's going to be the same voltage going this way. So this one, I'm going to go down a resistance. I got a resistance of 4 in that top branch. And so you say my delta V is going to be I times R, right? So it's going to be I times 4. Yeah. Go in the top branch. Go in the bottom branch, I have to have, brown branch, I have to have the same delta V, right? And so I have the same delta V here. And so then I have to, if the same delta V here to here, these have to be the same. So from here to here has to be the same as here to here also, right? You know, here to here is the same, and here to here is the same as here to here, so here to here is the same as here to here. So you say, well, wait a minute. If I'm going down voltage here, I'm going through 1 ohm and I get a delta V. If I got double the ohm, I better have half the current through this so that I get the same delta V as here. So having half the current, and I have to have the same delta V as this does, half the current, same delta V, I better have twice the resistance. This had better be a 6 ohm resistor. That's the way I'm thinking about it. 6 ohm, that's choice E. So 16 is going to be E. All right. Let's see here. Backside. Grab one more sheet of paper here. Okay, here's a circuit that says the battery provides a constant voltage V, right? When the switch S is closed, the value of capacitance is C, and the value of resistances are R1 and R2. Immediately after I close the switch, the current supplied by the battery is, you see, when I first close the switch, right, it's an uncharged capacitor. So there's no charge on it yet to resist, to block any flow or make it harder for charge to flow. So in the first instant, this acts like a bare wire. A bare wire across here would short circuit this resistor. So no current in the first instant flows to this resistor. The current's just going to be flowing like this. In the first instant, it's a circuit with just this one resistor. So at the first instant, it's just a little like, ignore this right branch because it's short circuited. And you say, oh, delta V is IR. And so, sorry, my I is that delta V, the voltage of the battery, divided by the resistance R1. So that's my current in the first instant. V over R1, that is choice B. Okay, 18. A long time after the switch has been closed. Okay, so if it's been closed for a long time, we can assume this capacitor is now fully charged. If it's fully charged, then no more charge is flowing to the plates or through here. If there's no charge flowing through here, then the delta V here from here, well, what am I saying? The delta V here has got to be, basically there's no current flowing here. All the current is flowing around the outside then, right? If it's fully charged, no more current flows here. So my circuit now, basically this capacitor isn't doing much. I just have this big circuit with current flowing around the outside. Yeah? And so I'm going to have my delta V, but now I'm going to go down R1 and then down R2, right? I got 2 voltage drops. So my delta V is just going to be, delta V is IR. Sorry, this is for this one. Delta V is IR. But my R is now both these guys in series, one and then the next. So it's my I times R1 plus R2, right, is my delta V. And I'm trying to find the current, so it's just going to be delta V over R1 plus R2. That's my current. And you say, hey, that's choice. My voltage, this is the voltage of the battery, which they're just calling V, sorry. The delta V of the battery, just calling V. V over R1 plus R2, that is choice A. All right. Here we've got this this circuit. Notice they've got a little current flowing this way, right? So into that low V side battery, out the high V side, right? 0.8 of an amp, 0.8, 4/5 of an amp, then a 20 volt battery, and then there's a little R, like, you know, you can imagine that's like the internal resistance of the battery, maybe, but anyway, it's some unknown resistance there, and then it comes here and it splits 2 resistors in parallel. 30 and 60 in parallel is shown to a battery of EMF 20 volts and internal resistance R. Yeah, it is your internal resistance battery. The current in the circuit is 0.8 amps. What's the value of little r? So I'm just trying to find that resistance, which is pretty much what I guessed from the picture I'd be trying to solve for. Here we go. So doing this, first I'm just going to go ahead and I'm going to simplify the circuit. This is a 30 and a 60 in parallel. So this chunk here, I'm going to use the 1 over formula, right? The inverse, right? The reciprocal formula for resistance in parallel, 1 over 30 plus 1 over 60. So that's 2/60ths plus 1/60th, that's 3/60ths, but that's 1 over. I'm going to flip it. 60 over 3 is 20 ohms. So my total resistance in my circuit, if I do now, I'm going to do just a delta V is IR, right, for this, for going around the circuit. My total resistance would be R plus 20. So the delta V, 20 volts, I'm going to go up 20, I'm going to go down 20 going through this stuff. So down 20 is my current, 0.8 times my resistance, that's 20 plus R, because this is in series with this. So I'm going to add that R plus the 20. I'm trying to solve for that R. We can do it now. again, like I said, this is like 4/5, right? Is what 8.8 is. So multiply both sides by 5/4. So that'll be 100 divided by 4. That'll be 25. Is 20 plus R. Hey, look, R is 5 ohms. And 5 ohms is choice C. Okay. And last question. Variable resistor. So it's a resistor you can change the resistance of. You can imagine, for example, having like maybe some long, thick, some wire that's made of some material that's difficult for, it's a conductor, but it's kind of a bad conductor, and charges have to burn off a lot of energy to wiggle through it. Well, imagine I have my circuit hooked up here, but instead of hooking there, I have like a little connector here to go to the rest of the circuit, and I can slide this. So if I slide this down, the current doesn't have to go as far through as much of this junk, and so there's less resistance. I slide the connector into here, now it's got to flow through all this to get to there. I've increased the resistance. It's a variable resistor. Okay, I've got a variable resistor connected across a constant voltage source. Which of the following represents the power dissipated as a function of its resistance? There's asking for the relationship between power and resistance if you got a constant delta V. So to have an equation that relates power and resistance and delta V to each other, you say, sure, the power equation, one of the forms of it is delta V squared over R. I think I used that back at the start of this test. So I want the relationship between P and R, constant delta V. Hey, this is just an inverse. P is proportional to 1 over the resistance. And so 1 over R graph, this is the one. So we want graph A. And that's the multiple choice. All right. So I probably should have done this at the start, but here, there. Okay, that's what my answers look like. Okay, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19. There's my answers. Okay, there we go. All right, I will do the free response.